Hello students and friends. This is now the second part of my lecture series discussing on test questions related to electrostatics. But this time we'll be focusing on analyzing electrostatic force, sometimes called Coulombic force, which is the kind of force exerted by two or more charges, or even the force between an uncharged body and a charged body. So just stick around and learn and watch. Alright, so first of all, we will define what you mean by electrostatic force. Okay, so the force of attraction between two unlike charges, or even between a charged body and a neutral body, alright, of course, that includes the force of repulsion between two like charges. Basically, by nature, this is known as electrostatic force. Okay. Uh, as a whole, it is a kind of fundamental force belonging to that, as you probably know, the four fundamental forces, such as strong nuclear force, the weak nuclear force, okay, the electromagnetic force, which this electrostatic force falls under, and of course, gravitational force. So we will just concentrate on electrostatic force. The word electrostatic also means that we will assume the charges to be at rest. Okay? And likewise, we state now, okay, the law that says it all. We call this Coulomb's law. It states that the magnitude of the electrostatic force, more commonly labeled as F sub E, meaning electrostatic force, that exists between two charges Q1 and Q2. And these Q are separated, or the two Qs are separated by a distance labeled small r, as shown in our illustration down below here. This force is directly proportional to the product of the two charges, okay, but inversely proportional to the square of the distance between them. So this relationship, all right, of the electrostatic force, okay, to the magnitude of the charges and also to the distance separating them, to the square of the distance that separates them, is summarized in this equation that looks familiar to many of you, I'm sure. All right, it goes something like F is equal to a constant K multiplied by the absolute value of Q1 and Q2. All right, so we are only concerned with the absolute value, whether or not the charges are or have their signs specified. But in using the formula, we just stick to this magnitude of the charges, and this will be divided by the square of the distance separating the two charges. And incidentally, the value of K that you are going to use in this uh, tutorial is equal to 9.0 times 10 to the 9. The unit is Newton meter squared per coulomb squared. All right, so we'll have our first example, okay, in a little while. For our first sample problem, find the magnitude of the force between Q1, which is equal to positive 1.0 times 10 to the negative 6 coulomb, and Q2, whose charge is negative 2.0 times 10 to the negative 6 coulomb, if they are 6.0 centimeters apart. So this is just a straightforward, okay, example of applying that formula earlier shown, all right, which is F is equal to K multiplied by the absolute value of Q1 times absolute value of Q2 divided by R squared. Okay, so we simply have this given data substituted in that formula, such as 9.0 times 10 to the 9th, okay, Newton meter squared per coulomb squared, that's the value of K. Then multiplied by the absolute value, see this slash symbol, okay, we mean only the magnitude of the charge will be substituted in here. All right, so 1, that's Q1, 1.0 times 10 to the negative 6, while the other Q2 is 2.0 times 10 to the negative 6, all over the distance r that separates them have to be, or has to be, converted to the SI unit, which is meter, and that is equal to 0.060, okay, meter, and then that will be squared. So with the help of your cycle, okay, you will be able to get this value for the electrostatic force. Okay, this is just the magnitude, as what's the question is asking for. Magnitude of the force, 5.0 Newton. But supposing you are also asked to describe, okay, what force does each charge exert on each other? So we say that a 5 Newton force, 5.0 Newton force exerted on Q1 by Q2 such that it makes Q1 attract or be attracted towards Q2 in as much as the two charges are of opposite signs. Okay, and it also depends on what the question is asking, if there is a need for you to indicate the direction by first showing the vector diagram, we can always do that. All right, but since the question is only asking for the magnitude, then it is simply as simple as this. All right, so what about example number 2? A 1.0 coulomb charge is 15 meters from a second charge, and the force between them is 1.0 Newton. So what is the magnitude of the second charge? So this time around, we are given the magnitude of one charge, and the second charge is unknown, and we are asked to find the magnitude of that second charge given the separation distance between the two charges, which is 15 meters, as well as the magnitude of the force between them, which is 1 Newton. All right, so again, we just transpose the, we just derive the formula by transposing the second charge, such as Q2, because that is what we are looking for. So our solution shows that working formula for finding Q2, and this is equal to Q2 equals the product of the force multiplied by the square of the distance divided by the value of the constant K multiplied. Okay, that K will be multiplied to the value of the charge of Q1. And substituting, we have 1 Newton multiplied by the square of the distance, which is 15 meters, all over the constant K, 9 times 10 to the 9. I did not include anymore the unit, okay, because it's kind of long. I will run out of space. So sorry for that. And then that will still be multiplied by 1 coulomb. But as we expect, okay, we are looking for the value of the charge Q2, whose unit, of course, should be in coulomb. But we also want to express it in a more commonly used unit, such as the nanocoulomb. All right? So using your cycle again, we will get this amount of Q2, 2.5 raised to the negative 8 coulombs. All right? So since we are not so familiar if this amount of charge is rather large or small, so we convert it to nanocoulombs and we get a whole number, 25 nanocoulombs. But take note, nano means 1 nano means 1 raised to negative 9 coulombs. All right, so I hope this answer makes sense to you. This is now example number 3. We have a figure that shows 3-point charges that lie along the positive x-axis in a vacuum. All right? Determine the magnitude and direction of the net electrostatic force on the charge Q1. Of course, we will use the value for K equals 9.0 times 10 to the 9th Newton meter squared per coulomb squared. So here's our diagram. All right. There's first we have Q1 in the middle. All right. Q1 whose charge is positive uh, 3.0 microcoulomb. All right. Take note, it's a positive charge. And to the left of Q1, we have Q2, whose charge is negative 4.0 microcoulomb. And they are 0.20 meters apart with Q1. All right. To the right of Q1, of course, we have the third charge, Q3, whose value of the charge is equal to negative 7.0 microcoulomb. All right, and we also indicate the distance between Q1 and Q3, which is 0.15 meters. Although they are not drawn to scale, but I make it a point that 0.15 meters will look as, shorter than 0.20 meters, especially in our next diagram, which we call vector diagram. All right, but our concern is only on the forces acting on the charge Q1. All right, and that is emphasized in our vector diagram, where only the forces acting on Q1 are indicated and labeled. So what are they? First, we have the force exerted by Q2 on Q1. Okay, exerted by Q2 on Q1. Notice how we label our force. Okay, F sub 21. 2 meaning where the force is coming from. So it's coming from Q2 and is exerted on Q1. Okay? The force exerted by charge Q2 on Q1. And why is it directed to the left? Because we see the charges of Q1 being positive while For Q2, it is negative. In other words, we say that Q1 is being attracted to Q2. So the force exerted by Q2 on Q1 is directed to the left. Okay, to the left, meaning towards Q2. So I hope that is clear why F21 is exerted to the left. Okay, as a force, which is a vector quantity, okay, the need to indicate the correct direction is very vital and important. Now, how about the force exerted by Q3? We label that here as F sub 31, meaning the force exerted by charge Q3 on Q1. Okay? Force exerted by charge Q3 on Q1. Why is it to the right? It is because, again, Q3 is negatively charged. So we say, therefore, that Q1 is being attracted, all right? Attracted towards Q3. So the force exerted by Q3 on Q1 is directed to the right or towards Q3. So in short, there are two forces, external forces acting on Q1, one to the left and one to the right. And the question is asking for the magnitude and direction of the net electrostatic force on Q1, net meaning the total. All right, I'm sure you have been through this when you discuss forces in Newton's three laws of motion. So, the concept of Newton's three laws of motion are still being applied in this topic. All right, so we are talking about concurrent forces such as F21 and F31. Okay, acting on the same charge, which is Q1. So it's only Q1 that we are analyzing in our vector diagram. All right, how do we calculate each of these forces, F21 and F31? Let's start. For F21, of course, we use the Coulomb's law formula. Okay, K times the absolute value of Q1 multiplied to the absolute value of Q2 divided by the separation distance between the two charges concerned, such as Q2 and Q1. All right, then substituting, we have doing away with the units first for simplicity. After all, we are expecting the unit of the force to be in Newton. All right, so that gives us 9.0 times 10 to the 9. That's the value for K. And the value for Q1 is 3.0 raised to the negative 6 because microcoulomb is 10 to the negative 6 coulomb. That for Q2, of course, is 4.0 raised to the negative 6 coulomb, all over the square of the distance between Q1 and Q2. And that happens to be 0.20 meters. Got to square that. Okay. And then again, with the help of your cycle, you will get for the value of F21, which is 2.7 newtons. Now, referring to your diagram, vector diagram that is, we know that this 2.7 newtons, okay, relative to Q1 is directed to the left. All right. So if you're kind of strict, all right, in your computation, you can probably specify here that the direction of 2.7 newton is to the left, or simply you can put here a negative sign such as negative 2.7 newton to indicate that it is directed to the left. All right, you can do that. Let's move on in the calculation for the other force, F31. Okay, for F31, the same method, the same formula to be used. We just substitute the correct values. For the quantities, you will notice they are exactly identical except for the value of Q3. All right, because we are now talking about the force exerted by Q3 on Q1. And the value of Q3, of course, is 7 raised to the negative 6 coulomb. So doing the same method of multiplying and dividing using your cycle again, we will get as the magnitude of F31 being 8.4 newtons. All right, so what do we do next? Of course, we will now add these two forces, add them vectorially, or get the net force. All right, so the net force on Q1 is just the vector sum of F21 plus F31. All right, now here we indicate the sign already because we are adding vectors. These two force vectors have to be indicated with their correct direction. To the left means negative, to the right means positive. And negative 2.7 newton plus 8.4 newtons will give us, of course, for the value of net force equals positive 5.7 newtons, or simply 5.7 newtons directed to the right. All right, to the right based on our vector diagram, meaning Q1 will have a net force of 5.7 newtons directed towards Q3. So it's like saying that the force exerted by Q3 is stronger, all right, stronger than the force exerted by Q2, which results to a total force equal to 5.7 newtons directed towards Q3. And I already anticipated or predicted that. That's why I was able to indicate that the arrow that will represent F31 should be longer than the arrow that represents F21, considering two things. All right. Before we arrive at this final net force, I already had the uh, what do you call this? I already had the prediction that F31 will be greater than F21. And you can always do that, okay, when you are solving problems. Okay. What are the two factors that you have to consider in determining the magnitude of the force? Of course, how far apart they are. Okay. So Q1 and Q3 are just 0.15 meters apart as compared to the distance between Q1 and Q2. That's one factor. The other is the amount of charge of Q3 is the magnitude, I mean, of the charge Q3 is 7 microcoulomb compared to that of Q2, which is 4 microcoulomb. So I use them as my basis in predicting that possibly F31 would be larger than F21, and my prediction was confirmed. Okay, that the force exerted by Q3 on Q1 is indeed greater than the force exerted by Q2 on Q1, which resulted to a net force of force amounting to 5.7 newtons directed towards Q3. I hope that is clear. We are down to the last example, example number 4. Three particles with charges Q1 equals negative 4.0 times 10 to the negative 6 coulomb, Q2 equals positive 6.0 times 10 to the negative 6 coulomb, and Q3, which is equal to positive 3.0 times 10 to the negative 6 coulomb, are placed at the corners of an equilateral triangle with sides of length 10 centimeters, as shown in this illustration. What is the net force on Q3? show vector diagram for forces on Q3. Alright, so here is the equilateral triangle, and each charge, according to the problem, is placed at the corners. So I just assume that Q1 is here, Q3 is on this corner, and Q2 is in that corner. Alright? And we are looking for the net force acting on Q3, which in my assumption, in my diagram, I put Q3 on this left corner of the equilateral triangle. Alright? So, the vector diagram will some kind of like this. Okay, it will look like this drawing here. How do I know that the force exerted by charge Q2 on Q3 is to the left relative to Q3? It is because when you look at the given charges Q2 and Q3, right? Q2 is positive and Q3 is also positive. So these two charges will be repelling each other. And since what we are after only is the force or forces acting on Q3, okay, as emphasized in this vector diagram, the force exerted by Q2 on Q3 is, it is as if Q3 is being repelled or moved away from Q2, hence the direction is to the left. And that is indicated by this arrow, denoted by the force F sub 23. Alright? How about the force exerted by Q1 on Q3? Alright. Look at Q1, it is negative, while Q3 is positive, so we are talking about force of attraction. Q3 is attracted towards Q1. Alright? And it looks like that the direction of that force is from Q3 going towards Q1. So that's labeled here as F sub 13. These are the labeling that we can come up with. Okay, we are told to show vector diagram for the forces on Q3, and this is how we do it. Which between the two forces is greater? Is it F23 or F13? Well, you can do your preliminary analysis. Okay, what do you think is the force, the magnitude of each force, by comparing, for example, the charges involved, okay, the charge of Q1 and Q3, and then the charge of Q2 and Q3, and then how far apart they are. Okay, but right now it's okay. What is more important is you're able to label the correct direction. All right, the correct direction of each of these two forces. So that's constitute the first part of our solution. Okay, showing the vector diagram, and in a little while we will go to the computation, or first, okay, we indicate the amount of charges Q1, Q2, and Q3. All right, here they are, just to make sure we won't make mistake in our substitution of this data into the formula. So already we have here the substitution for the given, for the uh, formula of the given data in solving for F13. All right. So 4 raised to the negative 6 coulomb, that is the charge Q1, just the absolute value. We do away with the sign. And for charge 3, Q3, we have 3 raised to the negative 6 power, that's coulomb, divided by how far apart they are. And since in an equilateral triangle, the sides are the same, so 0.1 meter, we have to square that, and we will arrive at this amount of force for F13 equals 10.8 newtons. Okay? And examining the direction of that force, okay, we know that in an equilateral triangle, all right, the angle of each, what do you call this, each corner here, or each vertex of an equilateral triangle is equivalent to 60 degrees, correct? All right, so with respect to the horizontal, we say that the direction of F13 is 60 degrees above the positive x-axis. Okay? How about for F23? That's the force exerted by charge Q2 on charge Q3. So we just again substitute. Okay? 6 raised to the negative 6 is the charge of Q2, and the charge of Q3, which is 3 raised to the negative 6 coulomb, divided by the same separation distance, and that is 0.1 meters. Square that. Again, using your cycle, I just labeled here the value of K. All right, it's understood that the whole thing will still be multiplied by 9 times 10 to the 9. All right, that's the value for K. And then, as a result, you will get also the value for F23 equals 16.2 newtons. And then the direction, if you look at your vector diagram, it is directed, okay, relative to Q3, it is directed to the left or to the negative x-axis. So we will continue our calculation because we are looking for the net force, and that will come in the last slide. Alright, so moving on with our computation. So again, we have the vector diagram. We need it, okay, to continue with our calculations. We already have computed the value of F13, and we got 10.8 newtons directed 60 degrees above the positive x-axis, and for F23, our computed value is 16.2 newtons towards the negative x-axis. So this time, we will get the net force or the total force. But since these two forces are not along the same straight line, all right? So there is a need for us, okay? Actually, there are two possible ways of determining their vector sum. Okay, one would require using a formula in trigonometry, which we call the sine law and the cosine law. All right. Those who are familiar with that, okay, you can use it. But what I'm going to present here is the method of using the components. We call it the component method, which means that between the two forces, F13, okay, has what we call a vertical and a horizontal component. All right. For the horizontal component of F13, we call it F13x. In other words, this F13 can be resolved into its x and y components. So, to get the x component of F13, we consider that angle that was earlier described to be 60 degrees. Right? And using the meaning of cosine of that angle, right? Because the x component will represent the adjacent side of that angle that we choose, and therefore we can define the trigonometric function cosine, because cosine 60 is just equal to the adjacent side divided by the hypotenuse of an imaginary triangle here. The hypotenuse actually corresponds to the computed value of F13, which is 10.8 newtons. Alright, so using your calculator again, cosine 60 multiplied by 10.8 newtons will give us 5.4 newtons, which has a positive sign because that x component of F13 is directed towards the positive x-axis or towards the right. Okay, how about its vertical component, F13 sub y? Its vertical component is directed to the positive y-axis or upward, and that requires the use of sine of 60 degrees, right, to be multiplied by 10.8 newtons, and we will get positive 9.4 newtons. Positive meaning to the positive y-axis. Now, for the second force, F23, since it's already directed to the left or to the negative x-axis, we say that its x component is just equal to that given F23 value, which is 16.2 newtons. Alright, but we just emphasize that it is directed to the left, hence the negative sign here. It has no vertical component. Alright, F23 sub y is equal to 0 newton. So, what do we do next? We just add the x components of the two forces, meaning 5.4 newtons positive, alright, to be added to negative 16.2 newtons, and we call their sum as the summation of Fx, and that is equal to positive 5.4 newtons plus negative 16.2 newtons, or simply minus 16.2 newtons, and we will get a summation of Fx that is equal to negative 10.8 newtons. The negative sign simply means that their summation is in fact directed to the left, alright, of the x-axis. Now, for the y, summation of Fy, alright, positive 9.4 newtons plus 0, of course, that will still be positive 9.4 newtons. Emphasizing again that this component, summation of Fy component, is directed upward or to the positive y-axis. So the last step is to get what we call the net force, because we are now left with the x and the y summation, alright, and therefore we can easily use Pythagorean formula, alright, which is F net equals the square root of the square of each component summation of Fx and summation of Fy, each of them to be squared. Alright, substituting the square of 10.8 is equal to 116.6. Alright, and the square of 9.4 is 88.4. And getting the square root of the sum, we will get 14.3 newtons as the amount of the net force. And what is the direction of that? Alright, since, as I said, okay, these two components will constitute the sides of a triangle, alright, a triangle which you can imagine like this. So the x component is labeled here as the red arrow going directed to the left, whose magnitude is 10.8 newtons, while the y component, which is positive 9.4 newtons, is in the upward or positive y component. And if you're going to add them vectorially or get the resultant force, which is labeled here by the black arrow, alright, that exactly is the meaning of 14.3 newtons. All right. The net force represented by this vector arrow, all right, directed somewhere between the north and the west, uh, what do you call, geographic directions, north and west. Or simply, we find the angle. We define an angle theta, all right, between that resultant force represented by the black arrow with the negative x-axis. So take note, if we define that as our angle theta, and then use the definition of tangent of the angle theta, where uh, we can use the formula for inverse tangent or arc tangent. We just divide the opposite side of the triangle divided by the adjacent, or 9.4 divided by 10.8. If you get that quotient and then get the arctan of that ratio, okay, to eventually get the value of theta, which is, using your cycle, we will get an angle that is exactly equal to 41.0 degrees. So we can use that angle theta to describe the direction of the net force. Okay, our complete answer therefore is F net is equal to 14.3 newtons directed 41.0 degrees above the negative x axis. Our drawing or vector diagram is shown down here. So I hope this problem, the solution for this kind of problem involving, okay, addition of forces that are not along a straight line, all right, two forces that makes an angle that is not equal to 0, or an angle that is not equal to 180 degrees. All right, something like this in our vector diagram. I'm sure you have been in this method of solving forces when you were discussing Newton's three laws of motion way back when you were still in mechanics. So that will be all for today. Okay, I hope to see you in the next tutorial, where we will be talking also about uh, electric fields. Thank you for now and have a good day.